Hey guys, welcome back to another episode of Simuleos. Today we're going to continue working on the Huffman integration scheme. Huffman integration? What? That's not what we're doing. Huffman encoding schemes. Kind of like what we were doing yesterday. We've got a good bit to do, and I'm pretty excited because I think we'll finish up the visualization of simple Huffman trees today. Now we can make it more and more complicated as we go along. That's fine. The main thing is we need to be able to visualize a few different things, and so we need to be able to make sure that our scheme, man, I'm so tired, that our scheme can visualize everything that we need. So let's go ahead and open up Zernal, and let's go from there. So, Zernal, and let's get started. So, like normal, the Huffman encoding scheme is pretty easy to understand, I think. It might not be, the easiest to understand, but it's pretty close. The idea is that if we have a list of, let's say, frequencies in which all the letters are coming in, let's say A comes in with a frequency of 0.7, B comes in with a frequency 0.1, C comes in with a frequency 0.1, and D comes in with a frequency 0.1, we simply add the lowest together all the time. So these guys add to 0.2, these guys add to 0.3, and these guys add to 1. And then you kind of label it 1 0 1 0 1 0, and you say A is 1, B is 0 1, C is 0 0 1, and D is 0 0 0. Then you just do the encoding and decoding from there. Now, here's the cool part. As of yesterday, I spent a good bit of time looking up the Vitter algorithm, and the Vitter algorithm is a dynamic Huffman encoding scheme. Now, the dynamic Huffman encoding scheme is pretty cool. I'm not all the way done. I don't fully understand it, but I can tell you that this visualization will definitely help in understanding how and why it works. There's always a situation. Okay. Visualization, in my mind, helps people understand difficult concepts. The Vitter algorithm is an incredibly difficult concept, I think, so far as I can tell. So I think this is a perfect thing to visualize because it will totally help people understand the concepts. The other thing too is I just finished uploading my latest YouTube video is now officially out. It's done pretty well for itself. It's got 200 or 300 views or something like that, and I think I'm pretty happy with it. It's obviously not going to get the 10,000 views in 3 days that my other posted, the eigenvector one, but that's perfectly fine, because I only have 770 subscribers right now, so it's fine. It's actually exactly where I want it to be. Okay, so what are we gonna do? Let's go ahead and talk about what we need to do now. So we have this idea of the tree, and we have the root node only. What we need is a priority queue. Queue. That is, how do we put it, organized by the weights of each individual node. This will put the lowest node first and the highest node last in terms of weights, and then we can just add them together, just like we would have to do in the traditional Huffman algorithm. So we basically add two together for a new node and draw lines to the new node, and that's all we need to do. It's actually pretty easy. So all we need to do then is we need to say, okay, well, we have two appropriate positions. Let's draw two lines to the new position. So we'd have a node here, a node here. Oh. We would add these guys together for a new node. Each of the nodes has its own weight. So then we just add the two nodes together for this new weight. And we'd say, okay, well, this guy and this guy, let's see, add to this guy, and I don't think it's gonna be that hard. I think we can figure it all out. Let's see, the only thing we're gonna have to watch out for is the fact that these guys are, how do I put it? These guys are held by their weight, right? And so we have to kind of think about the easiest way in order to hold the data to work with this system, but I think we should be able to get the internal nodes done today, and I'm pretty excited about that. From there, it's just a matter of figuring out how to again, make it look pretty. And I think it's going to look pretty enough to start with. We could make it look much better by, you know, adding in some curves and things like that. But for now, I think it's okay with what we've got. Okay, so let's go ahead and continue. I don't see very much more that we actually have to discuss. I realize I've been doing like 5-minute introductions for the past, you know, few days, but I think that's all we need. So, as a quick recap of what we did yesterday, we were officially able to, let's go over here and pop this over there, CD into projects, Simuleos, Huffman. And now let's take a look at the animations. Let's go into Mirage, Frames, Animation.gif. And you'll see, one second, let's make this a little bit smaller, that we were able to generate all, I think, 27 points, or however many points there were, 17, 27. Anyway, we were able to generate all of the points. Now we just have to add them together. So you'll see kind of like these guys down here. Those are the ones that we need to add together. How do I put this? Yeah, those are the ones that we need to add together first, and then we add together all the other ones after that. So we're going to see how it looks after doing that. So, how do we do the scheme that I was talking about earlier? Well, we've already done it once. So let's CD into projects, Simuleos Huffman. And the first time we did it, it took me some time to understand it. So let me go into vi huffman.cpp, and let's take a look at what we did. So let me go down to Q. Here we are. Node Q, node Q, node Q, node Q, node Q, node Q. Where did I put it? Oh, you know what? It's probably in vi Huffman. One second. .h. Okay, so I betcha I put it into node Q. Let me see, where's node Q? Node compare, node, Huffman CP, Huffman tree, using node Q. Oh, here we are, using node Q as a priority queue. There we go, that's what I wanted. So the node queue is a priority queue with a node. Let's see, vector of nodes and node compare, where node compare compares basically, you know, the weight. So basically read in a bunch of nodes, and that's all we need to do. So let's go and see what we did with this node queue guy. So let's go ahead and quit here, and let's go into huffman.cpp and look for node queue. Okay, so we have created the initial nodes, and we've set it as node queue. Okay, sounds good to me. That should be about it, right? I think node queue is a vector. So let me go in. Oh, I mean, node queue is a priority queue, so it's obviously a vector. So we need to do something very similar here. So let's go node queue, create nodes. That's fine. We need vector of character keys, vector of double weights, but we should have create nodes. Okay, so what we also need is a third node queue create nodes that goes through with the, how do I put it? Just the parent node. And this one's not going to be so bad, I don't think. I think it's going to be pretty easy to do. So let me see. Node queue create nodes with an unordered map and key weights. Okay. Okay, so let's do this. We're going to go down here. And we're going to say, what do I want to say? Here, let me go ahead and put this in the other terminal. Right, quit. And then let's go here and vi huffman.cpp. Okay, now let's go back down to where we were before. Node queue. Initial nodes, that's fine. Create nodes. Yep. Okay. So now we're going to basically copy this template up here. And we want a second overloaded create nodes function for root node. Okay. What do we need? It's going to be down here. Node queue. One second. QUE. Create nodes. What do we want? We want node queue. Okay. Oh, no we don't. We want node star root. Okay. I don't know why I did it that way. Okay. So what do we need in the node queue? We need a few things. So first we need to create node Q, and this is going to be, I guess we'll call it regenerated nodes. This time, one second, we are recreating the tree for later. Okay, so regenerated nodes, that's what we're going to call it. Why not? It's a long name. I don't really care. Return regenerated nodes. Okay, so this actually shouldn't be so hard. We basically perform a depth first search, and we go through and we add all of them together. So let me look at the depth first search algorithm that we put in. I think it should go through everything. Let me see. Depth first search. Where did we use this before? Root current bit string. Okay. What did we do? We did this to create bits, and this returns, let me see. Does it update bit strings? What does this actually do? It does a simple search, that's what I wrote down, but I failed to write down exactly what this means. Okay, so what are we doing? We're going through and we're saying if root right and root left, current key equals root key, okay? And then we say bit strings push back current. Okay, sounds good to me. So what we need to do then is a depth first search with the priority queue in it. Let me see, Huffman code point current, current.code, depth first search. Yeah, okay, so what we're going through them all, and we're saying if there is no right and there is no left, then what we do is the current key is going to be equal to root key, and then we push back current. Okay, that seems fine to me. Then what do? We say current node plus equals 1 if we are going to the right. Okay, so this is basically a recursive search through the tree, so we need something very similar here. Let's see, so we need to read in node root. Good. Yep, we definitely need to read in node root. What else do we need to read in? Let's go through and let's think. So we want node root, and let's create a second depth first search guy here. So we're going to do does a simple search to find. What do we want? To regenerate node Q from root. That's fine. Okay, I think I'm gonna have to do it this way. Let's do depth first search. I'm going kind of overboard with all these overloaded functions, I think, but that's okay. That's perfectly okay. For now, I mean, it's okay. Okay, so we need node root. What do we need? Huffman code point current. Do we even use current? No, I don't think we need current. Okay, and now we want to read in the node queue. Regenerated nodes. Okay. We can delete this line here. We do the same thing we did before. If root right and root left, we do current key is going to be equal to root key. And then we basically perform, let's see. One second. We then basically perform the depth first search with the right and the left. Now let me think here. I don't think... Okay, so this up here is saying if there is nothing to the right and if there is nothing to the left. That's fine. The node queue, let's see how we used it before. Let's see, node queue. Okay, Huffman node queue. Let's see, node 1. What are we doing here? So this is assuming we already have the node queue. Node queue regenerated nodes, node queue initial nodes, and let's see, what did we do here? We said temp node is equal to new node, key dot first, and then we say initial nodes push temp node. Okay, and then we return initial nodes. So basically we're going through all the keys. Let's see, what are we doing? Key weights, unordered map, key weights. We have characters, we have doubles. So basically with this create nodes functions, what we're doing is we have a map of all the characters and all the doubles. And then what we're doing is we're going through and we're checking. We're basically creating a new node and then we are pushing it back. So we're going through all of the everything in the map, which is called key weights, and we're going from there. Let me check my stream real quick. Okay, good. So again, guys, if you have any questions, comments, concerns, let me know. I'm going to go ahead and put up the animation on the side because we're not currently using this terminal of what we did yesterday. And then if you have questions on that, we can talk about that too. Again, any questions, let me know. Right now, we're just kind of creating some new functions to work with. Okay, so what do we have here? So up here, the first time we created nodes, again, we had some sort of map with all the key weights in it. So it's a dictionary, right? We went through every element in the dictionary and we created a new node and pushed it to the initial nodes, okay? In this case, we simply need to perform a depth first search and do the same thing. So let's perform a depth first search and push back the priority queue. Okay, seems good to me. So I think all we need to do is fix the depth first search command. So let's go down here. Where is it? Depth first search. Here. So this is going to be an overloaded depth first search command, and we're going to return this guy here. Okay, now all we need to do is the following. We're going to do depth first search. Okay. So we do current.key root key. We don't need this because we don't need bit strings in this one. So I don't think at any case we actually need to tell where, if we're at a leaf node, which is what that was doing. In fact, let me comment it up here. This is, are we on a leaf node? Okay, so now we have root right, current code +1. We don't need this. We don't need that. We don't need this. We don't need that. What we do need is following. Let's do, I guess it'd be up here. Yeah, I guess it would be up here. So let's do this and let's do regenerated nodes. Dot push, and let's do root. Okay, I think that's all we need to do there. Okay, so let's go here and say nodes, good. Okay, let's see if that works. So we're going to go up here, performs with an S. Oh gosh, I can't do anything right now. Okay, now we're going to say, I think it was depth first search. What did I call it? Depth first search, exactly that. So we want the following. Depth first search. And what do we want? I guess all we need is root and regenerated nodes. Okay, so now let's output everything in regenerated nodes at this point. Rather, let's return it and then we'll output it all later. So let's write this. What we need to do is put these functions now in Huffman.h so we can read them by the other, how do I put this? By Huffman visualization. So let's go into Huffman.h and let's see what we got. So scroll down here. Where are we? Simple decoding scheme. Does the encoding, simple search, that's fine. What do I want? I want to go up here to create nodes and I want to add one more create nodes. And this is going to be right here. Add in a semicolon. And then we also need to do one more depth first search. Open this up down here. And where are we? Here we are there. Okay, let's put that there. Okay, so now we're going to switch things around a little bit. We're going to go into Huffman.cpp here. .cpp, and we're going to go into Huffman visualization.cpp here. Okay, let's go down to main. And you'll see that we currently have things to draw all the animations and things like that. That's great. It is currently working. We're happy with that. However, I want to work on some other things real quick. So we have draw tree, we have Huffman tree, final tree. Let me, instead of drawing the tree and animating the tree, let's try something else for now. So let's go to main, and let's just see if these new functions that we created work. So we've already decoded. Let's do the following. Which ones did we just add in? We just added in a way to create the new nodes. So let's create a list of initial nodes. So let's do node queue, and we're going to call it regenerated nodes. And this is going to be equal to create nodes with the root node. Okay, and I think this is actually going to be, what do we want? Huffman tree, final tree, dot root. Okay, this should work. And now we just want to print it out. This is going to be in the main function. Let me see, where is it? In main, I commented it out. Let me see. I should have had somewhere in here the ability to output. Let me see. Huffman tree, void depth first search. What am I looking for? Hey Marion, how are you? Okay, depth first search is here, but I want to output my created nodes. It's kind of a pain, but that's okay. Okay, so the problem is that because we're in a priority queue, the easiest way to go through each of the elements is to pop them all out. So let me see, what do we have? Let me go over here and search for all the pops. Pop back. That's fine. Pop back. That's fine. Where are we? Initial nodes.pop. Yep, okay. So let me see. Let's try just outputting some things. I think I'm going to do this incorrectly, but that's okay. So we're going to say while regenerated nodes dot size. Again, guys, I'm not very confident with my ability to use priority queues. I apologize for that. Greater than 1. We're going to do the following. We're going to say, so this is what we're going to have to do in the end. We say initial nodes dot top, and then we say initial nodes pop. Hey Nakib, how are you? I know I always ask this when I suddenly pop on your streams, but what are you working on? I am currently working on visualization to the Huffman encoding methods. So here's the idea. Let's go ahead and write and quit. What we can do right now is we can generate all of the leaves, right? Now we have to draw internal nodes between the leaves, and this isn't exactly the easiest thing to do. Now you might be asking, why care about visualizing this? Well, it's because in the end, I want to start working on a rather difficult algorithm, and that algorithm is the, what do I say here? The Vitter algorithm. It is the dynamic Huffman encoding algorithm, and this one, I don't know, I just don't get intuitively. So what I'd like to do is create a visualization of it so it's easier to understand. Plus, I think it'll turn out really cool. I could just imagine like me saying things like on some sort of video or something like that, and then have the text kind of scrolling underneath and dynamically creating this Huffman encoding tree for what I'm saying as we are as we're going through. And then we just cover encoding and decoding, and I don't know, I just think it's kind of neat. 1 second. I'm getting kind of hot, so I'm turning on the air conditioner. Okay, so I'm really looking forward to how this turns out. I think it's going to look pretty cool. Again, a lot of the stream or a lot of my channel, I think, is kind of going 2D animation, but that's okay. I'm kind of learning how to do the 2D animation. One thing I'm not happy with my videos is the chalkboard stuff that I do at the start of my videos. I ended up doing that for the past 2 videos. For the eigenvector video, it worked okay. For the Monte Carlo algorithm, it worked okay, but it could have gone better. And I think it would have been better for me to just animate the text and everything with Cairo, since I know how to use Cairo, and it seems to be working quite well for animations. So I think my next video, which will probably be the Huffman encoding video, I'm going to try to have no chalkboard at all, and it's just going to be straight animations that we make, which I think should turn out okay. We'll see. We'll see. Okay, so while regenerated nodes.size is greater than 1, here's what we're going to do. We're going to output std cout. Then what do we want to do? We want to output regenerated nodes dot top. And then what do we want? We want, I suppose, weight. Sure, why not? New line. This is totally going to work. And then we do regenerated nodes dot pop. Okay, well, this is going to break in a number of ways. Let's just see what happens. Make. Okay, so current was not declared in the scope. Depth first search. Let me see. 173 of Huffman.cpp. Let's go into Huffman.cpp. And let's go to 173. Okay, depth first search. Fair enough. We want not this. I think we just need regenerated nodes? Yeah, we need regenerated nodes. Oh, wait a minute. We'll see what happens. I think this is going to do something stupid. And let's go down here and add regenerated nodes in. Let's go regenerated nodes. The board reminds me you have access to a classroom. For now. Make. And let's see what happens. So it says top.weight. Let me see. Do we not have a weight in node? vi huffman.cpp. Where do we... Oh, I guess it's huffman.h. Struct node, double weight. We do have weight. Let me see. Maybe we needed to point to it. Request from member weight, which is a pointer type. Okay. How did we do this last time? Sorry for the yawn, guys. Maybe we have to do it this way. Make. Okay, this seemed to do something. Now let's see. Let's see how many we have here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52. 52. We started with how many? Let's see, I think it was 27. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, so we have 27, and we end with 52. That is possible, I guess. Let's go with it. Sure, okay, I'll trust that. Why not? Why not? I'll say there's probably... That would mean that there's a total of 25 internal nodes. So we have 27 leaves and 25 internal nodes. Maybe that's right. Who knows? Hey, I care. Okay, so why not? Why not? Okay, so now we have to basically do the Huffman algorithm, but now visually. I don't know what happened with my hands there. Sorry about that. Okay, so what are we going to do for that? Well, we're going to do the same thing we did before with the... how do I put it? What am I doing? I don't know what I'm doing. We're going to do the same thing we did before with the general Huffman algorithm. It's just in this case, we are going to draw it out. And then what do we need to do? Basically, let me think. Yeah, we're just going to draw it out. See what happens. What's the worst that could happen, right? Okay, we have to animate the lines. We have a time at which we need to animate the lines. Sure, okay. What did we do before with the draw tree? We did draw tree and we did Huffman tree. Okay, that's fine. But let me see. Do I not want a time in which I want all of the Okay, so here's what I'm going to do. First, I'm going to update the draw tree command over here to give it a time in which I want it to draw all of the frames. So double time. Okay, and also, man, I was hot, and then now I'm cold because air conditioning's right there and blowing on me, but that's okay. So draw tree. So what do we want then? Let me go down to the draw tree command and see what we've got. So draw tree. Let me see. What did I say? Draw trees here. What did we say we want the time to be? Let me think. We have 30 frames, I think I said. Right? 30 frames? Oh, come on. 30 frames. 100 frames. Whoa. Okay. So 100 frames at 10 frames a second means 10 seconds. Is that correct? VI, what do I want? Mirage. There we are. Maybe it's close. Sure, okay. We'll go with 10 seconds. Okay. Where are we with main? Here we are. So we'll go with 10 seconds here. Okay, so we've got our 10 seconds. Now what do we want? Let's go down to the draw tree command. Here we are. Add in a double time. Good. Now, what did I do over here? I don't remember at all what I was doing with my life at this point. Auto key tree.bitmap, that's fine. Size t. For auto tree in bitmap, what are we doing? We're saying we are going to external nodes push back. Then we're saying grow circle. Here we are. This is what we need. So it's going to be 10 divided by external nodes dot size. Okay, well, we have a list of all the external nodes, right? So we should basically divide time by the total number of external nodes that we have here, right? And then each one of these should take that amount of time. Let's go here and do time. Okay, now let's go up to main again to make sure this works. Here we are in main, and I think I will leave it in for now. Okay, so node queue, regenerate nodes equals create nodes. That's fine. Draw tree. So let's go over here and let's make it. Let's see what we get. Looks to me like we generated everything. Good. And it looks like it's all in time. So let's do mirage animation.gif. Yeah, it's the same GIF as before, or GIF, or graphics interchange format file, whatever you want to call it. I think I'm just, again, I keep trying to call it graphics interchange format file, but like it's so long, and I don't know whether to pronounce it GIF or GIF, and I don't know. It's just so confusing. Maybe I should just quit and go off in my own little world where I call peanut butter GIF, and I don't know. Okay, so now we have to draw the Huffman tree in a visual way. So let's go over here to this one, and let's open up vi huffman.cpp. Now, the Huffman algorithm, let me see, what did we return from Huffman? We returned a node star from Huffman. Okay. So in the end, what we did is we returned what are we saying? We returned the root node. That's what we did. So what we want to do here, let me go up to the top. I'm going to create a void which is visual Huffman, or draw Huffman, I guess. Why not? Function to draw. One second. Function to draw internal nodes. So I guess we'll just call it. How about we call it void draw internal, and then we'll have a separate function later to draw Huffman. So we're going to say frame ampersand anim. Then we're going to say double time. And then we need the priority queue. So let's do priority queue. Oh, I'm sorry. It's called node queue. And what are we going to call it? Regenerated. Such a long name. Nodes. Okay. Looks good to me. Okay. Let's go down here and let's put it there. Okay, draw internal nodes. Let's go here, there. What do we need to do? I guess we just draw the nodes. Right? Okay, let's do it. Okay, so we're going to have node 1, node 2, and node parent. Let's do it that way. So we're going to do, what am I doing? Node 1, node 2, node parent. Okay, so now we just go through the entire list. While regenerated nodes dot size is greater than 1. And one big difference about this, guys, when compared to what I normally would do, so one big difference between a node queue versus like a vector or something like that, is that with the node queue, you can't, or rather, I don't know how to see internal nodes very easily. So instead what I'm doing is I'm actually destroying the node queue as we're going along, which is why I don't put an ampersand, or rather I don't want to put an ampersand, but I guess we could, for the regenerated nodes, just in case we need it later. So what do we need now? While regenerated nodes.size is greater than 1, we're going to do the following. We're going to say node 1 is going to be equal to initial nodes, regenerated nodes dot top. So we're taking the top node, then we're removing that node. So we're going to say regenerated nodes dot pop. It's going to pop the top node. Now we say node 2 is going to be equal to regenerated nodes dot top, and we say regenerated nodes dot pop. Okay, so now what we do is we say the following. We say node parent is going to be equal to a new node. Sorry about that, node. Oh, come on. And now we just add everything there. So we say basically the same guy we have here. Okay. Oh, what am I doing? Oh, dagnabbit. Okay, so let's copy this. Then we go down here and we link the nodes together like we did last time. Actually, we don't need to link the nodes in this case. It should be okay. Then what we need to do is the following. So now we need to visualize this new node with lines. Okay. And then at the end after that, we're going to have to do regenerated nodes dot push, and then we want to do node parent. Okay, so this time we don't really need to worry so much about returning the root node or anything like that. It's okay. We're just going to go through and we're basically going to draw some lines to the new nodes every time. And that's about all we need to do. So what do we need to do then? We need two different lines to draw. So let's go up here, animation double time, draw internal. What we're gonna need is, let me think. Let's go ahead and also read in a double that is the radius. And let me go up to the very top where we did the draw internal, and let's do it again. Draw internal. Okay, that's fine. There it is. And let's add in double radius. And again, guys, if you have any questions, comments, concerns, let me know. Chat, you guys can say anything you want. Totally okay. Well, within reason. Keep it family friendly, but within reason. And I will, totally talk as soon as I see it in chat. Okay, so now we need to basically draw lines to the new point. So we need to figure out where the new weight is. And what do I want to do? I want to say that, let me think. So is there a circumstance? Let me think here. We should probably also find a way to keep the positions of each node in the node struct itself. And I know, let me think. Does this make sense? I think it does. So let's go into the node struct and let's add in a position. So we're going to go into vi Huffman.h and struct node. Let's put this under the position struct. So let me see, where's... Wait, what? I don't have a position. I don't have a position. Wow. Interesting. Okay, fine. We'll just go in here and say double x, x, and y. Good. Okay, so now we have a position. When we are doing the initial external node drawing, where we find x position, what are we doing? Double find x position, temp x, temp y. So what are we doing? Temp position, double time, Huffman tree, frame anim, temp position, position. I totally have position defined. What? See, here I am. Look, there's a position. Fine, it's fine. This is actually easier anyway, but that's weird. Okay, anyway, I don't know where I defined position. Oops, sorry about that, guys. I did not mean to hit the microphone. My bad. Okay. So let's go through. We have temp position Y, temp position X, external nodes, pushback, temp position. That's fine. Okay. So external nodes, pushback that. And then what are we doing here? Oh, external nodes. What is external nodes in this case? External nodes is a vector of positions for external nodes. Okay, that's fine. So we have a vector of all of the external node positions. However, maybe what we should do, let me see, string bit string. Do we have the bit string? Parent, left, right, key, wait, other library. We have another library? Oh, we do have another library. Yeah, no, the position is defined here. Yeah, it's in this file, of course. Good, that's fine, that's fine. I defined it, I think, at the top of this file. Yeah, here it is, right there. Okay, you're right. Sorry about that, Marion. Okay. So we've got a couple of different things that we can do. First thing first, to find the x position, we need the bit string. Do we have the bit string? Not necessarily. No, we only have the nodes, and the nodes only have the wait and the key, and what they're connected to. So, let me think. We could do a number of things here. But if we just keep track of the x and y position, I think that should be okay. Let me think. I don't like... There's something I just don't like about this. So let's go through and let me see something. We found all of the x and y positions that we needed for all the nodes. And that's the grow circle command right here. Oh, just before the grow circle command, right there. If we knew, we can find, I think, the y position just fine, because the y position is super easy to find. It's just, well, just this guy up here, right? So that's not so bad. The x position is the one that I'm having trouble with. So let me see, if we kept the x and y positions here, then it wouldn't be so bad. And what we could do is up here, when we're finding the x and y positions, dang, see, that doesn't really make very much sense now, does it? I was thinking what we could do. So we have the x and y positions here somewhere, right? And we have a position external nodes. Where do we create the external nodes? Let me see. Let's go up to the top. Wait, where did I create the external nodes? Let me see. Node queue, decode, Huffman tree. I have find x position defined, but the problem is find x position is defined based off of having a bit string, which we do not currently have in the nodes themselves. So that's like your string of ones and zeros. So we'd have to put that into the node. And I'm trying to think if it's worth it or not. Let's see, so we have int max bit, and also max bit, which I don't know if we have either. So let me see, we have node queue, draw internal. Okay. Sorry for the yawn, guys. what I'd like to do is at this point here, go ahead and put an XY position into the node, because that'd be super easy. But I'm trying to figure out what I'm doing here. Draw tree is here. Then I create a vector of external nodes. Oh, I see. Okay, so I created a vector of external nodes here. Then I went through each of the keys. Okay, that's fine. Hey, Love Feelings, how are you? I'm doing great. Thanks for asking. Okay, so what we have here is we're going through all of the points. Wait, let me think here. If we have the nodes, we have this map, we have all the weights we need. Maybe we don't need to regenerate the tree. Let me think. Key map. Let me think. What we could do... Wait a minute, I'm trying to think here. We have our Huffman tree, right? Then what we do is we go through and we say the max bit... No. 1 second, I'm trying to think here. We have a bitmap in the tree. What else do we have in the Huffman tree? Let's go over here. Huffman tree. We have root. We have bitmap. And we have the encoded and decoded phrase. That's not going to help us at all. See, from the map, we don't have the weight. Dang. Okay, we're going to need to do something here. Okay, so let's recreate the depth for a search. And the depth for a search is now going to give each node an X and Y position. So let's go here. Sure, coding is difficult without, you know, a lot of things. But I don't know. Personally, I like coding without colors. It makes it easier for me to read the code. Rather, let me put it this way. It makes it so I pay more attention to formatting and things like that, so that later on, anyone who's reading it anywhere can read the code. Let me also remove these guys here. Okay, so what do I need to do? What I wanted to do was go into the, what is it? Which function was I going to look into? I was going to look into the create nodes function, the one that gives us our initial priority queue. And then when I was going to do that, and we did the depth first search, I wanted to go through and add in an X and Y position. Okay, so we have find X position. That's fine. So let's go into the depth first search guy. So let's go ahead and quit here. Okay, did I write anything? Yeah, I did. Write and quit. And let's go here and write and quit. Now let's go here and open up the node stuff. See what happens. So you can go vi huffman.cpp and let's go down to depth first search. Okay, I'm gonna try something that's probably not gonna work, but I'm gonna try it anyway. So depth first search, void depth first search. This is what I want, right here. Okay, so this is obviously a how do I put it? A recursive algorithm, right? So we continually go in and we go through a whole bunch of things. So what I'm going to say is I'm going to go up to the start and I'm going to add in a double, what do I want? X position. Okay, and let's put this down onto the next line. Okay, so we're going to read in X position. And I'm going to say, depending on which way we go, the X position changes a little bit. So let's remove it here. If node right. So let me go here and we're going to say node. So we have all the nodes. So let's go here and say, what do I want? I want, what am I doing? 1 second. I want root pointing to X. It's going to be equal to X position. Okay, so we do that and then we push it back. Then we go down here and we say we read in X position. And then we go here and we read in X position. Okay, so now let me think. We'll be on either the right or the left, so what do we need to change x position to in this case? Well, we change it to, if we're going to the right, oh, this is super complicated, isn't it? Dang it, I was hoping it'd be a lot easier. Because we don't know where we are on the tree, this isn't exactly the easiest thing to do. Okay, so let's go ahead and botch that idea. That was a dumb idea. Dang. The problem is we need to find the positions of the internal nodes. Again, you'd think that this would be super easy because we do have the positions stored somewhere, but it's not stored anywhere I think I can really easily get to. DD? Right here. You're using X position to find out if you go left or right. The node does hold the info. However, that's not the issue here. The issue isn't to determine whether we go left or right. To determine whether we go left or right, we already have the depth first search algorithm. Or not algorithm, but whatever it's called. And it just goes left and right and left and right. It's fine. That one works okay. The problem is I need to know the actual position. Because if we go here and we run Mirage, these are going to be all of the external nodes that we're drawing, right? So here's all of them. What we need to do now is draw the internal nodes. Finding a Y position is not very difficult because we just have to kind of say, okay, if it is of this weight, it is of this height. So the weight is directly represented by the height here. The problem comes in that we don't have these X positions stored in a very easy to find way. And so I'm trying to figure out a way to do that. So that's kind of the idea. They have an actual X position, but the X position is determined after the fact. And now we have to recreate everything. So let me think here. We do have all the X positions though. Maybe in the create nodes function. Where's the create nodes function? Huffman node queue, create nodes. Okay. We have the root node. Depth first search. And then we return back root and regenerated nodes. Dang it. Literally this entire create nodes function is just a depth first search, which doesn't help very much. Maybe there's a way. No, I don't like that either. Yeah, we have to tell if we're on an external node. Oh, maybe that helps us out. Okay, so we'll tell if we're on an external node. That's it. Got it. Okay, so we'll tell if we're on an external node. And then if we're on an external node, what we're going to do is we're going to say, now we have a character. We pull from the character to get into the map from before. And then we find the X position. Got it. Okay, so that's actually super complicated, but I think we can do it. So let's go into create nodes and let's add in a couple of different guys here. So one thing we need to add in, let's go into Huffman visualization.cpp. Okay, let's go down to the bottom here and let's see, what do we have? We have draw tree, find X position. Find X position requires the animation frame, which is fine. We can read that into create nodes. Then we need the bit string, which is fine. We can find it here. Do we actually use max bit? Max. Oh, sorry, I'm on the wrong terminal. Max bit. Max bit. There. Oh, I do use it. What do I use it for? Oh, I don't use it for anything. Let's go ahead and get rid of this. And then we don't need max bit anymore with X position. We only need the frame and the string. And that is something we can find. Good. So let me go up to find X position here. There, where else? Here, and let's remove max bit. Okay. Next. Remove max bit. This is super complicated, but that's okay. So now what do we need? Draw tree. And draw tree needs Huffman tree, frame, and I think that's about it. So for the, where are we? Create nodes function. I'm actually going to move this create nodes function into the Huffman visualization.cpp. Not that one. This one. And then I'm also going to put back the depth first search algorithm into this guy here. So let me see, what do I want? I want to put in this guy here. Let's see if it'll allow me to do this. I feel like this is really bad programming practice, but that's okay. For now, I think I'm okay with that. So let's bring this down to the bottom. Let's see. Yep, that's fine. Remove it here. Okay, what do we want? We want down here. Let's see, SD vector Huffman code points. I can remove that line. Unordered create bits. What do we want? Depth first search. Fine. Here it is. Depth first search here. G. Put it there. Okay, and I think we have create nodes. We have depth first search. That should be all we need. So let me add this up to the top of this code right here, so that we have everything defined. And I'm gonna have to put these into a header file in a bit, so we'll kind of do that soon. Trademark. And again, guys, if you have questions, I can definitely explain this a little bit better, but let me see if it works, and then I'll describe it in more detail after that point, if it's necessary. We go down here and remove this guy, node queue, this guy. You have an idea, but I can complain since I'm also doing programming to solve my own problems. Okay, about programming practices. Yeah, I'm sorry. This is pretty bad programming practice at this point. I did way too many overloaded functions, and I totally get that. In fact, let me go into huffmanvisualization.cpp and let me change the name of these guys, because I really don't like overloaded functions unless they're necessary. So we're going to say regenerate nodes here. And depth first search. I think this one we can leave the same. So let's go down here and let's change this to regenerated nodes. Regenerate nodes, sorry about that. And we'll kind of work on this in a second. So, okay, what do we need to do now? We have node queue regenerate nodes. And what did I do? I said draw internal. And where did I put create nodes? I know I used it somewhere. Node parents. One second. Create nodes. Wait, do I not use create nodes? Node queue regenerate nodes. Ah, regenerate nodes. Good. Now we go down here. And I can remove that. Similar to create, similar to create nodes. Okay. Good, that works. Visualize this new node with lines. So, what we need to do, we're regenerating nodes, and it just performs a depth first search. So, I had the idea. What we need to do is we need to read in stuff. What do we need to read in? We need to read in a couple of different guys here. So, first thing we need to read in is frame anim, which will be modified, kind of. No, it won't. But it's fine. This is faster anyway. Okay, now what else do we need to read in? We need to read in the Huffman tree, I think. But I think the only thing we need to read in with the Huffman tree is the map itself. So let me go into huffman.h. And let me go down to Huffman tree. Oh, it's right there. We just need the unordered map. So let's go ahead and add that in here. Oh, I already had insert mode in. Oop. Okay, let's go here. I think you must now change the regenerated nodes variable. We'll see. So we want std unordered map of the following. Character, bitmap. Good, so now that we have the bitmap, we then need to read this into our depth first search. And this is where I think things get a little bit weird. So also I added a semicolon. Let's go ahead and remove that semicolon. Now we're going to go down here and we're going to add that into our depth first search. Okay, so now the depth first search, we have expositions in the node now. So we have to do something to go from the bitmap to the regenerated node. So what we're going to do is we're going to say if root right and, I'm sorry, not root left. So this basically means we do not have anything to the left or the right, and which means we are on a leaf node. On a leaf. Okay, now we go through and we say, what do we want? We're going to have a string, and this string is going to be determined. Yeah, okay, this should be right. So then we have find x position, and we can basically put the x position in there. What do we need for x position? We just need the bit string and the frame. So let's go down and let's add the frame in, and hopefully this will work. Good. So depth first search, we need node root, and let me add in frame anim on top. Anim. Okay, so we're gonna have to change it up here, but that's okay. So let's go here and let's change it to anim root, and then we're gonna do bitmap. And then we're gonna go here and we're gonna say, I guess we can define the string in here, std string, and what are we gonna call it? Bit string. It's going to be equal to, I guess it's going to be bitmap of, what do we want? Root key. 1 second. Oh, okay. Then we need an additional if statement in here. And it's going to be if, what do we want? There is a root, 1 second, key. We do this. Oh, what am I doing? Else every other node should have an x position. What are we going to do? If it doesn't, then what do we do? If it doesn't have an x position, it should have an x position. Here, let's just do it this way. Let's find x position and then let's go from there. We're going to say root, what do we say? Root dot x is going to be equal to find x position of, what do we want? Where are we? Find x position, and then we need to read in the appropriate variables, which are going to be anim, the frame, and also the bit string. Okay, so now we should be able to find the x position. So this is going to say, are we on a leaf node? So let me think. There could be a situation. Let's see, find x position. If we are on the right. Wait, I need to think about this a little bit. So, if root right, what do? We say depth first search. So we continually go through right and left until we hit the end nodes, right? So we hit 2 leaf nodes, and then basically all we do is we add them together. That doesn't make very much sense, does it? Oh, we're pushing them all back. I see. So we're pushing 2 nodes back. But I guess as long as we have an initial x position to start with, we should be good, right? So we're starting with the root node, then we're going back. Yeah, so this should be okay, I think. Yeah, so let's try this. Okay, so we have some x positions, the only x positions that we have to start with, which should be okay. Okay, so we have this. I think this is maybe going to compile. Let me see. Well, first of all, let's go ahead and change. Let's go to the very top of this guy, and let's go down and change how we have defined these functions. So regenerate nodes, that's fine. dd, here, there. Now, regenerate nodes has obviously changed. Oops. Anyway, regenerate nodes is fine. Regenerate nodes. There. Where are we? There. Okay, let's add an additional guy there and add some semicolons in. Okay, let me see what happens if we make it. It's gonna break it, but that's okay. Yep, totally broke it. Let's see. Okay, we have expected a comma or something. Let me just go to 74. What do we have? Regenerated nodes, double radius, draw internal. Expected initializer before void. That's fair enough. Error, expected a comma, 84. Let's see. Node queue regenerated nodes. Character. Oh. Well, that's a little weird, isn't it? SD on map. Okay. So let's go down here. Yep, same thing happened down here. Okay, let's go ahead and write that. Let's make it one more time. And let's clear a couple times. Now let's make it again. Int made node final tree root. What are we doing? 125. Node queue regenerate nodes. Regenerate nodes. Oh, we need a couple of other guys here. So we need frame. Oh, we just need anim. I'm sorry. And then what do we need? Final tree.root. And then we want final tree. 1 second. Final tree dot bitmap. I think that was the order. Okay, what's next? Let's go ahead and see. No matching function fall for depth first search. Fair enough. So where do we do that? Regenerated nodes, I believe. Wait, what? Regenerated nodes. Oh wow, I getting kind of bad with these naming schemes, but that's okay. Regenerated nodes, draw internal. Where are we? Regenerate nodes. Okay, depth for search, anim root. Oh, that's wrong. Let me see. What's happening here? 441. Let me clear. Let's try it again. Make. Okay, no matching function call for depth first search. 438. Depth first search. Fair enough. We're gonna need anim. Root right. Node queue regenerated nodes. And bitmap. Yep, that looks right to me. So we're gonna do anim. Here. Root left, regenerated nodes, and bitmap. Make. And it made. Woo! Okay, so now we're converting everything, but that should be fine. It looks like we are going through everything just fine. So now we need to do the draw internal. We have an hour-ish, so hopefully we can get this done. So visualize the new nodes with lines. What are we doing? Regenerated nodes, pushback node parent. Okay, now we're getting to the hard part of the draw internal, which is that we have to draw all of these lines. So how are we going to do that? Well, I guess we just do it. Okay, so visualize the new nodes. We have all of the weakest nodes, right? And right now they're all external. So what we're gonna say is if they should all have position X's. Yeah, let me see. Yeah, they should all always have position X's. Because right now, the only nodes that we have, let's see, we have node 1, node 2, and node parent. What did we read in? Double time, node 2, regenerated nodes. Yeah, so right now, wait, how am I doing this? We have node parent. Wait, we might have too many nodes. Node parent, new node. Weight is going to be the weight of the two added together. And here's what we're going to do. We're going to say node parent dot x. So we just drew all of them with internal nodes, right? Maybe we didn't. Oh, wait a minute. Maybe we didn't. 1, 2. Where are we? So here are all the nodes we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wait, what? That doesn't make any sense. Let me think here. What did we just output here? I don't think that's what we wanted to output. Let's go ahead and delete this. And let's go up to the depth first search algorithm up here, rather main. And let's, where are we? Where's main? Oh, we're not there yet. Dang it. Let's go to here. Okay, now what we're gonna do is remove this line and this line. Okay, let's go ahead and write. And then we're gonna go over here and make it one more time. And this should output. Oh, it's after draw tree. Okay, so see how we have a whole bunch of different internal nodes? I've got a feeling that we don't want these internal nodes. Not at this point. So let me go down and let's fix that. So I think we only want the external nodes right now, which are going to be the ones with the lowest weight. So let's go and see if we can do that. I think we have external nodes, right? How many characters do we have in Jack and Jill went up the hill to fetch a pail of water? No idea. Okay, so let's go down to the bottom. Depth for search. We basically say regenerate nodes push root. What we need to do is only push root if we're here. So this means that we only have, let's do this. We only have external nodes. Now let's go ahead and make this one more time. Okay, now let's see how many nodes we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Bam! External nodes. I just hit my desk. Sorry about that. Okay, so let's go through and let's work on it from here. Draw internal. That's where we're at right now. So what we're going to say is node parent dot x. Oh, I'm sorry. Pointing to x is going to be equal to node 1. Let's do it this way. Node 1 pointing to x plus node 2 pointing to x. Then we're going to divide that, or multiply it by 0.5. Yes. Okay, and that should give us an x position for all of these guys. So now we should have x positions for everyone. What we need to do is visualize the new guys here. So we're going to say next is node parent. 1 second. Let me think. We'll have bit strings of a particular size. How do we find the y position again? Find x position. Let's go here and add a y position 2. So we'll say temp position y here is going to be key second size divided by max bit. Oh, we need max bit for that. Well, what's another way to do this? We have all the x positions, right? So how do we... Oh, we have a weight. Duh, we have a weight. Okay, so now the new y position is going to be related to that new weight. So what we need to do when we do draw internal is we need to read in max bit. And let me see, do we have max bit determined? Draw tree. Huffman tree. So what we need to do then is go through and in the draw internal, let me see. Draw internal here, we should probably, instead of reading in, wait, what am I reading in here? Node 1, node 2, anim, visualize regenerated nodes dot size, node queue regenerated nodes. Oh. Anim time. Let's also just read in the Huffman tree here to draw internal. I realize this is a lot of stuff to read in, but that's okay for now. We'll call it final tree, just as we have. Let me go to the draw internal function at the very top, and let's add this in. So let's go up to void draw internal. There, and there should be one more there. Correct. Huffman tree. Okay. So we're going to be reading in the tree. So let's go to draw internal. And what do we have here? Oh, good. So I haven't actually used it yet. So we're going to say node 1 is going to equal that. Let's see. How do we find the Y position? Well, we have the final tree. So let's go up here and let's refine the max number of bits. This doesn't take so long, so I don't feel so bad for doing it. Here. Actually, let's do this. There. Creating positions. Okay. Let's add this down here to the draw internal function. And we'll go from there. There we are. So now we have the max number of bits, which is great because now we can basically create the Y position. So how did we do it before? We did it with, where are we? Temp position Y, here. So I guess we'll do the same thing there, just a little bit differently. Okay, so let's pop down here. Where are we? Ah, here it is. So node parent Y is going to be equal to this, which we're going to modify. So instead of key second size, we're just going to say node parent dot weight. Let's go here, node parent dot weight. Oh, pointing to weight. And then we divide it by max bit. Fair enough. And then we multiply it by these guys, which I think is fine. To leave those as they are. Okay, so now we have an XY position for the parent node. We have an XY position for all of the sibling nodes or children node or whatever they're called. So I guess now all we have to do is draw the lines, right? So I guess we'll do that. We have time. Okay, I can't see anything that could possibly go wrong here. It's going to break in a bit, but that's okay. Visualize the new node with lines. So here's what we do. We say Cairo move to Basak Ma. What are those coefficients? Which coefficients are we talking about? There are a lot of coefficients here. Some are these coefficients, like the 9 and stuff like that. They're arbitrary right now. We'll kind of fix them in a bit. For now, basically they were set so that they would, or everything would definitely remain on, 1 second. This guy. So we do the animation. So yeah, they're definitely for scale. In fact, if you look at them, it's like 0.9. So what we did is we multiplied it by 0.9, so we shrunk it a little bit, and then we shifted it over a little bit. So that's all we did. So otherwise it would just be times anim.resolution y. But we kind of shrunk it and moved it a little bit. Okay, visualize a new node with lines. Okay, so we have the X and Y positions of the new node. Let's just kind of do it. So drawing first line. We have the radii. So let's do the following. If, what am I doing there? If node 1, let's do, what do I want? Oh, I see. So this is going to actually be not the easiest thing to do. We need to move to, so because we have to draw diagonally inward, right? So let me think. We need to move to a certain position, and that certain position is not defined right now. So let's just draw it differently, and then we'll worry about defining those positions in a bit. we can say Cairo move to. And what do we want? We're going to read frame context of animation.currentFrame. Okay. Then we say the two positions we want. So this is going to be node 1. I'm sorry, yeah, node 1 pointing to position X and node 1 pointing to position Y. Now we say Cairo line 2. Yep. Rather, draw line. How did I do the draw line command before? Let me see. Draw tree. Where's main? Should be up here somewhere. Grow circle, animate line. And we want, yes, the two origins. So let's go here. And let's just kind of copy this command and do it correctly. Again, I apologize. I just hit the mic again. This is totally going to break. That's okay, though. It's okay. Animate line. Good. Draw tree. Find X position, draw internal. Here we are. So this is a command we're emulating. So instead, let's move to this position here. Animate line. Yeah, that should be okay. So we do animation current frame. 0.5, no, this should be time divided by, oh, we don't know how many we're going to have to draw, do we? Let's just divide it by 20 for now. And then we're not going to worry about it. Okay, so we want Ori and Ori 2. So now we're going to say, instead of this Cairo move to, let's go here and say Ori, position, 1 second, position, origin, and origin 2. We're going to go down here and we're going to say origin, ori.x is going to be equal to node 1 pointing to x, and then we're going to say ori.y is going to be equal to node 1 pointing to y. Do the same thing with ori 2. Ori 2 is going to be equal to node 2 pointing to x. 1 second, I forgot the x up here. Good. And let's, gosh, I just cannot type right now. And then we do ori 2 pointing to .y pointing to equals node 2 pointing to y. Good. So now we're drawing a line between the origin 1 and the second origin, and we're saying the radii are 10, but instead of 10, I'm going to put in radius. And radius here. Let me just do this. I don't care right now about formatting. 1 second. Well, I guess I do care about formatting because I'm clearly doing this. Okay, so draw one line. Boss like Ma, I forgot a semicolon. I appreciate that. Okay, so let's go down here. Thanks, both of you guys, for telling me about that. So now we define a new origin, and we are going to say, what do we want? Oh, I did this incorrectly. Node 2, Ori 2, node 2, underscore. I feel like I don't need an underscore, but besides, I screwed this up anyway. This is node parent. And this up here is node parent. Then we draw it again. So let's go down here. What do we have? We're going to say, 1 second. How am I going to do this? We're going to say Ori. Actually, the same guy up here, really. So we're going to change Ori.x. And it's going to be node 2 instead of node 1. Node 2. Node 2. Okay, now we're going to animate line one more time. And this should be correct. Now all we have to do, so that they both draw at the same time, is we give it a different frame. So we're going to say current frame, which is the frame that we're currently on, but we want to subtract a few frames, and the number of frames that we're going to subtract is going to be, let me add a 0.0 at the end of 20. 1 second, 20. Okay, So the number of frames that we're going to subtract is going to be time divided by 20, which is going to give us a time frames per second, and then we multiply that by animation.fps. So we're going to say subtracting out time divided by 20.0 times animation.fps. Add in a couple of parentheses there. And then I think we can just watch it break. Let's see what happens. So what we need to do now is draw internal. So we already have draw tree. And we need to change the name of that command to draw external, but that's okay. So now we go here and we do draw internal. And we need animation and a few other guys. What else do we need? We need double time, node key regenerated nodes, radius, Huffman tree, and okay. So we want time, regenerated nodes, radius, and final tree. So animation, let's go here and say time, regenerated nodes, and Huffman or final tree. Okay. Let me go up to the top and add 100 frames. Let's go over here and let's make it and break it. Okay, cannot convert Huffman tree to double for argument. Let me see, what did I do? I missed something, didn't I? Let me go draw internal. Draw internal. Radius is what I forgot. That's fine. That is totally what I forgot. Regenerate nodes, and then we do radius of 10. Thanks, Marion. Make. Okay, tree was not declared in this scope. Auto key tree 392. 409 seems pretty easy, but let's do 392. Okay, for auto key in tree, I think it's final tree.bitmap. And then the last one we need is 409. Here. Node parent, and it says I forgot something. Expected a semicolon before the yep, I see the problem. One second, let me check. Find X position, find Y position. Double max bit. Oh, I see. Yep, I see. Let me go here. I put the parentheses in the incorrect spot. So let's see, this goes over here. Now we make it one more time. Radius was not declared in the scope. Draw internal radius, 134. I think it's 10. Make. It's making. It did something. I'm not sure what it did, so let's take a look at the animation. We're drawing all the nodes, and it didn't do anything afterwards. Shoot. Let's take a look. So let's go into Mirage, frames, animation. Well, how many frames did we get through? Oh, I have animation draw frames commented out. Let's make it one more time. And then let's see what happens. Okay, here we are making all the images, converting it to a graphics interchange format file. See what happens. Okay, so now we're going to do Mirage animation.gif. Here we are drawing all the nodes. They're all being drawn. And then nothing happens. Great. No, I don't want to close that one. Okay, let's see what we got here. It looks like at some point, I'm just not drawing the lines. Is it because, let me see, what did I do up here? Draw frames, animate line. Okay, let's output some stuff. So we're outputting a lot of stuff right now. Let's go ahead and remove a lot of these COUts and change the ones that we're outputting. So let's not draw frames anymore. I've got to do some quick checks with one thing or another. Okay, so let's find the next cout. SU cout PNG ID. That one's fine. What's the next one? Those are all commented out. comment it out. Animation.current frame. Comment out the circle and draw only the lines. Yeah, that's probably a good idea. So we'll do that in a second. Draw tree. Okay, so let me go to a few more things here. I should be C-outing a couple of different things, but I'm not sure what I'm C-outing. So it looks like regenerated nodes should be the first thing I'm C-outing. So let's go there. Animate line, regenerate nodes. Okay, depth first search. SD string. Wait, what? Regenerate nodes. Oh, you know what you know what? I'm fairly certain I know the problem. Main is here. Let's fix this up real quick. Let me try this. I'm fairly confident that this broke something. Yeah. Let's see what happens. Now let me do Mirage animation.gif. Drawing all the nodes and... Okay, we are drawing lines. We are totally drawing lines. But they're not being drawn correctly. Okay, let's see what's up. Yeah, those are incorrect. Okay, so let's see what we're doing. Are the X positions correct? I can't even tell. The Y positions are clearly wrong. But I thought maybe the X positions could be correct. Okay, animate line. Gosh, this is all in a day's work for broken simulations. Maybe we should change the channel name to just like fail or failed simulations or something like that. Okay, The other thing is they're drawing the wrong way. Anybody else know? They're totally drawing the wrong way. Okay. So let's go through and let's see if we can figure this one out. So this is in the animate draw lines. What am I doing? Grow circle, animate line, draw tree, draw internal. That's what this is in. So let's see if we can figure this one out. So we're clearly generating X and Y positions. Otherwise this wouldn't be happening. The Y positions are going crazy. Let me think. What are we reading out as weights here? Can the weights... Failure, I guess, is always an option. You're totally right. I'm trying to think here, though. I think the weights, in this particular case, are going over the max number of bits that we have in our bitmap. So let's go through and let's output a couple things here to check, to see what's going on. So I'm going to do what I was going to do before. Let me go up here to the top, rather to main. Oops. Main. And let's not output some stuff that we don't need anymore. So let's not draw the frames. Let's not draw the tree. Let's only do draw internal. Okay, so now we're going to go down to, and also regenerate nodes. Yeah, that should be okay. So we're going to do regenerate nodes. Let me think. If we already have a Y position for if we already have a Y position, let's think. The Y positions should simply be one Y position plus another Y position. However, I'm trying to think here. How did I define the new Y position? I defined it as... let's go down to draw internal. Actually, let's make it real quick. Actually, write it first, then make it. And let's see what we output. So we're outputting this step up front, which is fine. And then we're converting it, which doesn't make very much sense in this case. So let's go ahead and go into the make file and remove that. So let's go into make file and remove this conversion. Hey, Witty Bants, how are you? Okay, so what are we going to do? Let's go down to draw internal. void draw internal. Okay, so what are we gonna do? Frame, animation, double time, node queue, regenerated nodes, double radius, Huffman tree, final tree. The weight. Can the weight at any point grow bigger than the size of a string? Yes. It most certainly can. Yep. In fact, in some sense, I feel like it has to. Right? Let's think. So let me go over here. Let's draw out a tree. Page, new page before. Okay. See, now I'm more confident in the X positions than I am the Y positions. So here's what we got. Let's say we have, I don't know, 1, 2, 3, 4. Very simple. Okay. The length of these strings are going to be 2 each. However, these guys are going to connect. These guys are going to connect. These guys are going to connect. So even with the simplest tree, right? These guys are of size 2. Oh, wait a minute. Wait a minute. I think I did this wrong. Yeah, I think I totally did this wrong. Okay, so here's what we need to do. We need to give these guys a Y position. Okay, now how do we determine the new Y position? What I was doing before was this. So let's see. Let's say we have a tree that looks something like this. So we'll say page, new page before. Let's give A probability of 50%, B a probability of 25%, D a probability of, I don't know, 1, E a probability of 0.1, and F a probability of 0.05. Okay, so these guys are going to add together 0.15. These guys are going to add to 0.25. These guys are going to add together to 0.5. And these guys are going to add together to 1. So 1, 0, 1, 0, 1, 0, 1, 0. A is going to be 1. B is going to be 0, 1. C is going to be 0, 0, 1. D is going to be 0, 0, 0, 1. Yep. E is going to be 0, 0, 0, 0, 1. And F is going to be 0, 0, 0, 0, 0. I added a 0. No, I didn't. That was correct. 0, 0, 0, 0, 0, 0. I did add a 0. What am I doing wrong here? 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Oh, I missed D. Or C. My bad, guys. Let's erase all this. D, E, F. I don't know how I can't do the alphabet anymore. Okay, so A is 1, B is 0, 1. So what I said is the maximum length of the words is going to be 4. That's the max word length. Okay? And this means we have to traverse the tree once, twice, 3 times to get there. So 0, 1, 2. 3. So that's 4. We have to traverse it basically 3 times to get there. So that's what I did. Now, what we need to do then is, let's say we add these 2 guys together, E and F. Then we take the maximum number, or the maximum bit length. And then after giving the maximum bit length, we then need to say, okay, we go 1 stage up from that. So I think I have incorrectly created these Y positions. So let's see, what do we need to do then? We need to say how far down the tree we are, and that will give us our Y positions. So I guess we just code this up in a way that makes some sort of intuitive sense. So let's see if we can figure out how to do that. Parent Y is node parent. Wait, that doesn't make very much sense here. So what do we need to say? We have the size. We have the Y positions. What if we store Y not as a double, but as an integer? Okay, and it is as high as we have traversed up the tree. I don't know if I like that one either. Because there could be a situation where we add two nodes together and they go super high up the tree, right? Okay. So, but I guess this is just a first order approximation, right? So maybe this will do okay. Besides which, every single... Wait. Let me think. There has to be a way to do this with weights. What we could do is we could just continually add all of the sizes together. Let's try this. So what we're going to do is instead we're going to say max bit is going to be plus equals. Now let's go over here and make it. Oh, let's go up to main. This is not gonna work, but hey, it might work okay. Let's go. We were just in main. What am I doing? Here we are. We want to draw a tree. We want to animate frames. Let's go. Make it. Okay, we're gonna see what happens. Generate 200 frames. Super quickly, but that's okay. Oh, okay. Let's make it again. Let's make it clean. Then let's make it again. Okay. This is going to break. But that's okay. Sometimes we want things to break. You know what I mean? I don't know. I don't actually know what I mean. Let's go to Mirage. Okay. Let's see how we're drawing these lines. We are drawing a whole bunch of lines. I'm not sure what we just saw. Okay, there are all the points, and then here are all the lines. Yep. Okay, so we do have all the weights. Let me think. We have all the weights, but those weights do not at all correspond to the positions in which we're placing all the particles. Huh. Okay, so if you guys have any ideas, let me know. At this point, I'm really kind of at a loss. I don't even know if the X positions are correct because I feel like I can't tell. It looks like they could be correct, but I have no idea. Okay. So let's think. No matter what, let me think here. Man, it's just ugly. Okay, so let's draw this another way then. Go down to the bottom. So the same thing we were going to do before. I'm just at a complete loss here, guys. I have no idea what to do. Draw internal. Max bit plus equals key second size. So this means we have a giant number of... We have a giant total weight, right? Which is totally fair because in the end, we should have them all kind of add up to 1, right? So what are we doing? We are, first of all, adding these guys upside down. I just now realized that. So if we put these guys... If we flipped these guys, would they look okay? Let me see. It looks like we don't even draw them all. Let's go down here. Instead of time divided by 20, let's do time divided by... Oops, sorry about that. Time divided by, I don't know, like 100. I don't know. I'm getting desperate here. Okay. So let's do over here, make, let's see what happens. Oh, these are so broken. Okay. 1 second. Mirage animation.gif. These should draw a good bit faster. No, they're drawing at the same speed. Why are they drawing at the same speed? They should not be drawing at the same speed. But actually, they're not all drawing at the same speed. Okay, so that's another bug we have to figure out how to fix. Oh, no, it's not. I bet you I know the problem. One of them I'm animating super quickly. The other one I'm animating super slowly. Okay, let's go here and let's do a make real quick. Okay, now let's see what happens. And I might take Marion's suggestion and just, yeah, remove the drawing of the actual nodes. So, Mirage, animation.gif. Let's see what we got. Oh, oh, look at that. Look at that. It actually draws something. Okay, so this says to me that the, I don't know what it says to me. I really don't. Yeah, I have no idea. Okay, but this says to me that maybe the Y positions are just flipped around, right? And that we could find a way of actually putting these guys into an appropriate spot. So let me just try regenerating the initial set of points. So what I'm going to do up here, when I find the Y position, draw tree. Let me see, temp position Y. Here's what I'm going to do. I'm going to mess with this a little bit. Max bit. It's going to be equal to plus equals key dot second dot size. Right, this go over here. Okay, now let's do make. Okay, let's see what it does. It's gonna break two. Let's do Mirage. Okay, so now we're drawing all the positions up here, and when we do this, it's still broken. Darn. But it looks almost closer, in a way. In a way. Yeah, those X positions are off. But how far off are they? That's the question. So let's pull it up. Let's do Mirage. Frames. Image. Let's just start at the very first image. Okay, so here is our image in here. Let's just scroll. So here we're generating all the points. See what we got. Okay. All right. So, let's give this guy a radius of 0. Let's go down here. Draw internal. Let's see what we got. So we want animate line. No, we don't want animate line. What do we want? Oh no, this is what I want. I want radius of 0 and radius of 0. Let's go down here. Radius of 0 and 0. Okay, let's make it again. This is gonna break again, but it's okay. You know, we didn't really fix anything, so it's expected to break. The X positions could be right. I have no idea. I really have no way of telling. So let's go to this, and let's just scroll down. All the X positions are created, and aha, look at that, guys. I'm not sure what it's doing. Don't you want to animate line from one position to another? Yes, I sure do. And that's kind of what we're doing here. Okay, so we're creating all the circles. And what are we doing next? I'm not sure what's happening behind here. Just not sure. X position Y. Let me see. Position X. The radius is the size of each individual point. So the radius is the size of these dots here. So if we put on the radius here, let's do that real quick. So if we put on a radius like it was before, let's see here. Radius. Radius here. And down here too. Okay, write this, go over here and make it. What ends up happening is that there is a gap in between the lines and the dots. Here, I'll show you what I mean. So last time you saw that the lines connected. Here they will not connect. So if we scroll down, see they have a gap, and that gap is the radius of the circle. So the idea is that they don't enter the radius of the circle. Okay, so let me do it again without a radius. So the positions are not defined very much at all by the radius. But because we do want them to connect in the end. So I don't know, it's kind of a weird thing. We're gonna have to think of a way to do it differently. Okay, so let's change this to a 0. And actually I have an idea of how to make it so the external nodes have radii and the internal nodes do not. That's why I wrote it in there to begin with. Because, yeah, we'll talk about it in a second. Okay, and we could also make internal nodes be drawn, except be drawn with a smaller radius. So let's do Mirage. Yes. Scroll down. Okay, so my question is, what's happening here? And for that, I just don't know. Where are they coming from? Where are they going? I don't know. Eventually they draw down, which is what you'd expect, but I don't know. There's this weird stuff that's going on up here that I just don't understand. It looks like we're drawing, see, from Y position. Where would the Y positions be at that point? Parent Y is equal to node parent weight. Let's see, node parent weight is equal to node 1 weight plus node 2 weight. Oh, I betcha. We don't have the original positions defined in Y. Okay, so let's go through here and let's define those positions there. What do we do? We're going to say, let's do node 1 equals regenerated top. And then we're going to say, what do we want? Node here. Node 1. Pointing to Y is going to be equal to basically this guy right here, except for the nodes, or node 1 instead of node parent. Node 1. And then let's do the same thing for node 2. They're going to copy this guy, put it down here. Oop, screwed that one up. And let's do node 2. Node 2. Write this. And now let's make it. I think this will fix the problem of all of the nodes starting off at some random point. Then we just have to worry about how to make it look better. So let's do Mirage here. Let's scroll down. And yes, okay. So now, oh. Huh. Well. Huh. It's almost there. Here, let's open up the, let me see, what do we want? Let's do Mirage frames animation.gif. So here we have all the points being generated. And after all the points are generated, you then draw internal nodes, and it seems like it works for some of them, but not all of them. So, huh. We got to think about how to do this in a different way. And it also seems to me like not all the nodes are being given the appropriate Y position to start. So let me go up to where we are drawing the initial Y positions. Let's see, draw tree. Where are we? Draw tree, that's what I wanted. The Y position is going to be equal to double of key second size, which is the number of, what is it? It's the number of times this element is used. Okay. Then we do, where do the X positions come from again? How did I determine those? I don't remember. We used find X position. Oh, I see. Yeah, okay, that's fine. The X positions were defined. Okay. So Y positions. we have a situation where it seems to me that some of the nodes are not in the appropriate Y position. That it just seems to me like they're not being generated in the right spot. See, like these guys over here, for instance, especially that one guy on the far right. So here, let me open up this and let's scroll down to the very bottom. Yeah, so it seems like this guy should be way up here, and this guy should be up a little bit. These guys should be up a little bit. It just looks to me like we're not appropriately positioning all of the points to begin with, which is a little weird considering we're using the same equation, it looks like, to draw both of them. You know what I mean? Okay. So let's go through and see if we can figure this one out. Well, we have like 5 minutes, so we might not be able to figure it out, but we'll see how far we get. So auto key tree bitmap. Temp position Y is going to be double of key dot second dot size. Yep, that's the number of... Oh. Wait a minute. The weight is directly opposite of what we put down here. Shoot. Okay, well that's good to know. What we put down here was the size of the string, which is not at all related to the weight. The weight is, I mean, kind of what determines the size of the string to begin with, but the size of the string is going to be much, much less if we have a higher weight, right? So we have to figure out how to do one of two things, and I think what I'm going to do is I'm going to draw this weight-based first, and then we'll go from there. So how do we get the weight in here? We have external nodes, vector position, external nodes. The external nodes only gives an X and Y position. Okay, that's fine. How do we get the external positions? I see. So we have Huffman tree, which has all of the, let's see. So all this is doing. Okay, so how do we do the Y position then? So all this draw tree is doing is it's creating a list, I suppose, of, yeah, I screwed this up big time, actually. We'll fix it tomorrow. But here's what I did, just for the record. Okay. Actually, no, wait. We could have used that last slide. So here's what I did. And this is really, really stupid of me. Okay. I'm going to put down in red the weights. Okay, so this is going to be weight, let's say 1, 1, I don't know, 2, 3, 4, or something like that. I don't know, something to this effect. Okay, so the weight here is going to be 2, the weight here is going to be 4, the weight here is going to be 7, and the weight here is going to be 11. Okay, now the length of the strings, if we add them all together, is not going to be 11, which is exactly what I did. I said 1, 2, 3, 4 plus 1, 2, 3, 4, that's going to be 8, plus 3 is going to be 11, plus another 3 is going to be 14. And then somehow I just decided, oh, we can mix up the weight and the string length just fine. But we can't. I was being really stupid there when I was doing that to begin with, but the more you program, the more you learn. Is that a phrase? It should be a phrase. That's the phrase of this channel. Anyway, guys, I realized I kind of screwed up with this today, but we can continue working on it tomorrow, and actually we did make significant progress. I'm very happy with how far we got. We are now at the point where we can foreseeably draw these internal nodes, and we can do that tomorrow. What I'd like to do is get this visualization done soon, probably tomorrow or the next day, and then we can move on to the Vitter algorithm. However, depending on what you guys want, I was thinking about also taking some time to work on a side project for my next video instead of doing the Huffman algorithm, because I feel algorithms are kind of hard to do. The quieter you become, the more you're able to hear. That's about right, actually. But guys, it's kind of up to you. I'm going to put a poll on Twitter in the next few days related to what you guys might want for my next YouTube video. On the one hand, I do really like the idea of going through algorithms. On the other hand, I want something that I know people will enjoy. And so I had some requests after the eigenvector video to do things on like determinants and super simple things like that. And then we could, sense the lurking from my part. Well, actually, Marion, you're doing a lot of talking. So, I mean, not so much lurking. Okay. Anyway, guys, Danny McGee, you enjoy the algorithms. Okay, so we'll see. Again, I'll put a poll on Twitter for what I'm thinking about doing for my next YouTube video. Huffman trees will be up there. I'm pretty excited with how these visualizations are turning out, and I think it'll look really, really cool. That said, it will take a lot of animation to get done, because I want to try some new things instead of doing what I have been doing for the last few videos. Anyway, guys, at this point, it's 7 o'clock in the morning. I'm going to go ahead and end the stream here. There's a lot left to do. I realize that. But it's going to take some thought on my part. And so this is probably a good place to kind of end it for today. As always, have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where we finally get the internal nodes drawn. And then we start just messing with things, you know? Should we work on... Should we start working on the Vitter algorithm? I don't know. We'll see how far we get. These personal hair dryers don't fix themselves. Screamer Chaotix. I am also working on my PhD, just in a different way. Anyway, see you guys around. Have a fantastic day. Or night, evening, whatever. See you guys. Bye.